KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, okay, we start with the 28th problem here. You know, in this 28th problem, first to see the problem. Consider DT reaction, right? Deuterium tritium fusion given by the equation, that is H21 plus H31 gives rise to He42 plus N. Okay, next A. See here we are two things are there, A and B. So both we have to find. Okay, right. A. Calculate the energy released in million electron volts. Calculate the energy released in million electron volt in this reaction from the data. Okay, so this is the data given, that is what you know, for H21, H31 and He42 and N, right? That is what they have given here. You know, that is mass for H21 is like 2.014102 AMU, and then mass for H31, right, is like 3.016049. Next, that is for He42 4.002603 AMU, and that is for last, you know, that is what Mn, right, 1.00867 AMU, right. So all the mass values they have given in AMU. This is the given data, and based on this reaction, that is what DT reaction, deuterium and tritium reaction. And this is the equation, you know, H21 plus H31 gives rise to He42 plus N, right. So regarding this data, now we have to calculate the energy released in million electron volt, okay, right. And first I will finish A, then we will go for B. Why? Because after B means again you may forget what is there in A, right. So first I will concentrate on A. Calculate the energy released in million electron volt in this reaction from the data. Okay, right. See here, you know, the net reaction will be like this, no, that is what H21 plus H31, right, H21 plus H31 gives rise to He42 plus N10 plus Q, right. This is what net reaction. Okay, energy released in the reaction is, right. So that is what you have to write Q as a subject. Then, you know, this is what here and this is what here, and this goes that side, that is what minus, and then minus Mn because of neutron. Okay, right. You know, this is the reaction which gives us energy. I mean, by substituting these values according to the given information, we will get the Q value. That only he is asking to find. Okay, right. See here, adding and subtracting 2 ME, we get, see here, that is what H21, you know, plus Me, and that is what H31 plus Me, and this is what 2 Me, right, and minus Mnc square, right. You know one thing here, that we have to see from the mathematics point of view, okay, right. So that's why just adding and subtracting. So you know very well, in one equation if you add and subtract the same quantity means there will not be any change in the equation numerically, right. Mathematically there is no change, any change in the equation. That's why, you know, as simple as such we can write like this. Okay, next Q is equal to m of H21 plus m of H31 minus m of He42, right? Anyhow, mass, this is what H21, H31, He42 mass, and this is what mass of neutron into C square, okay, right, is equal to, see, we have to substitute. So whatever the values they have given, 2.014102 plus 3.016049, that is what they have given for H31, and minus He42 means 4.002603 minus, that is what Mn means 1.00867 into this we are writing in terms of million electron volt, right? So this is what 931 MeV, 931.5 MeV, to get this whole value in million electron volts, okay, right? After that, this process is pure mathematical, and here if you do this process, there you will get it as, this is, it will be like, right, this value will be given like 0.018883 into, as usual, 931.5 MeV, right? And if you do this, that is what, I am not saying anything here, just what I am saying is, you do this mathematical process, you will get some value and multiply that value with 931.5 million electron volt. So that you will get it as 17.58 million electron volts, okay. So this model is very important for us. So what is that model means? Having one reaction and calculating the amount of energy released, So this model is very, very important for board point of view, and even for NEET point of view also this model is important. It's a very basic model, but it is important. Next, B, see here. Consider the radius of both deuterium and tritium. Consider the radius of both deuterium and tritium to be approximately 2 Fermi, okay, Fermi meter, right? What is the kinetic energy needed to overcome the Coulomb repulsion? What is the kinetic energy needed to overcome the Coulomb repulsion, right? To overcome the Coulomb repulsion, right? To what temperature must the gases be heated to initiate the reaction? Okay, right. See here, consider the radius of both deuterium and tritium to be approximately 2 Fermi. Full stop. What is the kinetic energy needed to overcome the Coulomb repulsion? Okay. And there is one more thing. That is what to what temperature must the gases be heated to initiate the reaction? So we have to calculate. Okay, temperature, and before that we also need to calculate, that is what kinetic energy. Okay, right. See here, that's what I want to say here. If you observe carefully, see the solution, that is B, right? A completed, no? Now it is for what? B. See here. Distance between the nuclei when they almost touch other is, suppose for example this is one nuclei and this is another nuclei, right? So it is the radius of this nuclei and radius of this nuclei. Then finally what is the distance between these two nuclei, which is 2r. And they have given, that is what, 2 Fermi, right? So that is what the radius of both deuterium and tritium to be approximately 2 Fermi, right? And then what can we write? 2 into, right? That is what 2 into 1.5, right? 2 into 1.5 into 10 to the power of minus 15. 2 into 1.5 into 10 to the power of minus 15 meters is equal to 3 into 10 to the power of minus 15 meters. 3 into 10 to the power of minus 15 meters, right? This is what the distance between the nuclei when they almost touch other is. When they almost touch other is. Okay, that is what ma 3 into 10 to the power of minus 15. 3 into 10 to the power of minus 15, right? Minus 15 meter. See here. Next, one more thing. That is what repulsive potential energy of the two nuclei. Repulsive potential energy of the two nuclei when they almost touch each other. When they almost touch each other is, you know this formula therimo. We know very well this formula, 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught into Q1 Q2 by D. Q1 Q2 by D. Okay, right. And the value of 1 by 4 pi epsilon naught we know 9 into 10 power 9 into Q1 Q2, right? Q1 is 1.6 into 10 to the power of minus 19 no, right? So and one more Q2 is there, but it is same no, the charge is same. Then you can say that is what 1.6 into 10 to the power of minus 19 into 1.6 into 10 to the power of minus 19. So that you can say it is as 1.6 into 10 to the power of minus 19 whole square divided by 3 into 10 to the power of minus 5, sorry, 3 into 10 to the power of minus 15. Do this calculation, we will get it as 7.68. 7.68 into 10 to the power of minus 14. 7.68 into 10 to the power of minus 14 joules. This is the potential energy, that is what the repulsive potential energy of the two nuclei when they almost touch each other. When they almost touch other. Okay, right. Next, see here. That is what you know kinetic energy required for one fusion event. Kinetic, you can write this statement. You can write this statement based on the situation. Kinetic energy required for one fusion event is equal to average thermal kinetic energy available with the interacting particles. Average thermal kinetic energy available with the interacting particles. Okay, see here. Kinetic energy required for one fusion event is equal to average thermal kinetic energy available with the interacting particles, that is 2 into 3 by 2 kT. 2 into 3 by 2 kT, and here that is what if you observe carefully here, okay ma, see here, that is what average thermal kinetic energy available with the interacting particles. See here, that is what 2 into 3 by 2 kT ma, that is what 3 kT will come. Then next step, 3 kT is equal to whatever the value we got here, 3 kT is equal to 7.68 into 10 to the power of minus 14 joules, right? And you do this calculation mathematically, you will get it as 1.85 into 10 to the power of 9 Kelvin. That is what temperature, right? That only he is asking. So he is asking that to what temperature, right, must the gases be heated to initiate the reaction. That is what 1.89 into 10 to the power of 9 Kelvin, right? So it is a huge amount of temperature because it is 10 to the power of 9 Kelvin, right? Even though you take that is what 185 by 100, so it is 185 into 10 to the power of 7, right? So 185 into 10 to the power of 7 means, once you imagine how much big the value is, okay, right? So in first problem, that is what in this class, in 28th problem, in first case, that is in case A, that is two things are there, A and B. In A, we calculated the energy released in million electron volt in this reaction. So that is what this is the reaction from the given data, okay. So that energy we calculated as 17.58 million electron volts, right? In B, he is asking to find, that is what how much kinetic energy needed to overcome the Coulomb repulsion and after that to what temperature must the gases be heated to initiate the, that is what the reaction. Okay, right. Next, see here, this is what distance between the nuclei when they almost touch other, d is equal to 2r, that is equal to 1.5, right. 2 into 1.5 into 10 to the power of minus 15 meters, that is equal to 3 into 10 to the power of minus 15 meter. Afterwards, repulsive potential energy of the two nuclei when they almost touch other, that is what 1 by 4 pi epsilon naught into q1 q2 by d, right, and substitute the values, so whatever we have, and finally we will get it as 7.68 into 10 to the power of minus 14 joules, right. And now kinetic energy for one fusion event, right, is equal to average thermal kinetic energy available with the interacting particles, so that we can write 2 into 3 by 2 kT, that is equal to 3 kT, right. So when it is 3 kT is equal to this value, because this is also energy, no, repulsive potential energy of the two nuclei when they almost touch each other, right. So 3 kT is equal to 7.68 into 10 to the power of minus 14, 7.68 into 10 to the power of minus 14 joules. T value, because that is Boltzmann constant, we know 1.38 into 10 to the power of minus 23 joule per Kelvin, and then the temperature value we will get it as 1.85 into 10 to the power of 9 Kelvin. Next, see here, next problem, that is what 29th problem. Obtain the maximum kinetic energy of beta particles and the radiation frequencies corresponding to gamma decays in the decay scheme shown in the figure. That is, you are given that these are the values they have given, that is for AU 198, okay, and that is the value is 197.968233 AMU, and that is for HG 198, that is 197.966760, right. So this is the data they have given, and we have to see the picture. This picture is also part of question, and he is asking obtain the maximum kinetic energy of beta particles and the radiation frequencies corresponding to gamma decays in the decay scheme shown in the figure, right. So these are the energy levels, and one is 0.412 million electron volt and another one is 1.088 million electron volts, right, and it is AU 198.79, and it is beta 1 minus beta 2 minus, which is, that is what gamma 1, gamma 2 and gamma 3, okay. So this is about the picture. After completion of that, we are going to see the answer, that is what we are going to calculate, that is what maximum kinetic energy of beta particles, okay, and the radiation frequencies also. See, that only he is asking, no, obtain the maximum kinetic energy of beta particles and the radiation frequencies corresponding to gamma decays in the decay scheme shown in the figure, okay, right. See this one, see here, that is what the frequencies of gamma radiation, right, the frequencies of gamma radiation, see here, the frequencies of gamma radiation will be equal to the corresponding energy differences divided by Planck's constant, okay, that is what the value of Planck's constant, okay, and here he is saying that the frequencies of gamma radiation will be equal to the corresponding energy differences divided by Planck's constant h. And here itself, this is what E2 minus E1 is equal to h nu. From Bohr's postulate also you will get it as E2 minus E1 is equal to h nu, right. Now we are going to calculate for gamma 1 and gamma 2 and gamma 3, okay, right. See this. So that is what when in case of gamma 1, see this. So gamma 1 means this one, no. So this one and this one. 1.088 minus 0 into 1.6 into 10 to the power of minus 13 divided by this one, that is 6.63 into 10 to the power of minus 34. Right? It is million electron volt. Million means 10 power 6 and electron means that is 1.6 into 10 to the power of minus 19. So instead of that he has written directly 1.6 into 10 to the power of minus 30. Okay, right. And denominator, that value 6.63 into 10 to the power of minus 34, and we will get 2.627 into 10 to the power of 20 Hz. 10 to the power of 20 Hz. Okay, right. Afterwards we are going for gamma 2. That is what here in case of gamma 2, which is 0.4, these two 0.412 minus 0 into 1.6 into 1.6 into 10 to the power of minus 13 divided by 6.63 into 10 to the power of minus 34. The process is same, that is what E2 minus E1 by H. Okay, and here the answer is, that is for in case of gamma 2, 9.949 into 10 to the power of 9 Hz, 10 to the power of 19 Hz. This is what 10 to the power of 19 Hz. Okay, so it is 9.949 into 10 to the power of 19 Hz. Then for gamma 3, right, it is 1.088. See here, this is what gamma 3. Okay, 1.088 minus 0.412 into 1.6 into 10 to the power of minus 13 divided by 6.63 into 10 to the power of minus 34, that is equal to 1.632 into 10 to the power of 19 Hz, right. So these are all the frequency values for gamma 1, gamma 2 and gamma 3 based on this formula. Okay, and this picture also important and this value is also important. Okay, right. Next, now we are going to calculate the kinetic energy. The kinetic energy, that is what maximum kinetic energy of beta particles. Okay, right. See here. So first one, the beta 1 decay can be represented as, the beta 1 decay can be represented as, 198.79 AU gives rise to 198.80 Hg, right, and plus E0 minus 1 plus Q of beta 1 minus plus Q of gamma 1. This is the reaction we have. The beta decay can be represented in this manner, right, and here Q of gamma 1 is 1.088 MeV, 1.088 MeV, that is what the value of Q for gamma 1, 1.088 MeV. Okay, right. See here, and here the maximum kinetic energy of beta 1 particle, the maximum kinetic energy of beta 1 particle is, that is what K maximum beta 1 is equal to this value, and then this will come this side, that is why minus, and then this value also, that is what 1.088, because here we are writing in terms of C square, observe carefully, not MeV, that's why he multiplied with 931.5. And a small thing here we have to keep in mind, we neglected the rest mass of beta particle. Okay, right. So anyhow, by neglecting the rest mass of a beta particle, this is the expression, this is the equation you can write for maximum kinetic energy of beta 1 particle, and then we have to substitute the values, that is for AU, this value 197.968233 minus this value, that is what 197.966760 plus this one into 931.5 MeV, 931.5 MeV is equal to 0.284 MeV, 0.284 MeV, right. That is what here we got maximum kinetic energy of beta 1 particle, maximum kinetic energy of beta 1 particle. Okay, right. Next, similarly we are going to calculate it, similarly we are going to calculate beta 2 particle. That is what, beta 2 minus can be represented as, right? So that is what how we have written here, and similarly we are going to write the next thing. This is for beta 2, right? And AU 198.79 gives rise to Hg 198.80 plus E0 minus 1 plus Q of beta 2 minus and then plus Q of gamma 2, right? Where Q of gamma 2 is 0.412 million electron volts. Now, the maximum kinetic energy of beta 2 particle is K maximum of beta 2 is equal to, this is the expression we have to write, see, this is as it is, and this comes this side, that's why minus, and this one, that is what, 0.412 divided by 931.5. 931.5 into C square, and then you substitute the values, right? And then you will get this is, and then 0.412 divided by 931.5 into 931.5 million electron volts, okay? And if you do this process mathematically, finally we will get it as 0.960 million electron volt, okay, right? So in this class we discussed two problems. Both the problems are important, right? Both the problems are important. In first problem we focused to calculate energy released in million electron volts by giving a nuclear reaction along with some data. In B, in the first problem in B, here we calculated, right? We calculated the kinetic energy needed to overcome the Coulomb repulsion, right? So regarding deuterium and tritium, we calculated the kinetic energy needed to overcome the Coulomb repulsion. Thereafter we calculated the temperature must be, right? The value of temperature must required for the gases, right, heated to initiate the reaction. To what temperature must the gases be heated to initiate the reaction means, which is 1.89 into 10 to the power of 9 Kelvin, okay? So if you go to the answer, here in case of A, this amount of energy is released in million electron volt, 17.58 million electron volt, and thereafter if we are going to calculate to what temperature must the gases be heated to initiate the reaction means 1.85 into 10 to the power of 9 Kelvin. In the second problem, he asked to calculate maximum kinetic energy of beta particles, right? Maximum kinetic energy of beta particles and the radiation frequencies corresponding to gamma decays in the decay scheme shown in the figure, right? So that's what we calculated here for gamma 1, gamma 2, gamma 3, and then maximum kinetic energy of beta 1 particle as 0.284 million electron volt, and then maximum kinetic energy of beta 2 particle is 0.960 million electron volts, okay, right? Thank you. In our next class we will continue with next continuing problem, that is problem number 30. Thank you.